Hello and welcome to today's Tube versus Pipe Tech Talk presented by Swagelok Central Ontario and Atlantic Canada, one of more than 200 authorized Swagelok sales and service centers located around the world in 70 different countries. I'm Tim Phillips, Marketing Manager, and leading today's Tech Talk is our Mechanical Solutions Engineer, Phil Daniels. Before we get started, a few housekeeping items. Please use the live event Q&A feature for all questions. Questions will be answered periodically throughout the session. If you have further questions after the completion of today's Tech Talk, please direct them to Phil Daniels, whose email is on the screen, or the technical support team at your local Swagelok Sales and Service Center. We understand through extensive global research and first-hand experience that businesses are under pressure to do more with less, to maximize system performance while juggling smaller budgets, skilled labor gaps, and changing safety requirements. The COVID-19 pandemic only adds to the pressures. Swagelok and its sales and service centers like Swagelok Central Ontario, Atlantic Canada are here to lend a helping hand, to provide you with the right resources at the right time. Swagelok Central Ontario, Atlantic Canada has 3 locations: Mississauga, Ontario, Ottawa, Ontario, and St. John, New Brunswick. And we provide local engineering and technical support across Central, Eastern, and Northern Ontario, as well as all of Atlantic Canada. We are one part of an extensive global network of Swagelok sales and service centers that are here to help you with your applications and share knowledge through our extensive training and system evaluation offering, much of which we're adapting to provide virtually to you. Whether you need help with an application or to improve your knowledge in a specific area, whatever your pressure, think of us as your solutions provider. Now I'd like to pass it over to Mechanical Solutions Engineer Phil Daniels to lead the Tube versus Pipe Tech Talk. Phil, take it away.
Thanks, Tim. So like Tim said, my name is Phil Daniels. I'm a Mechanical Solutions Engineer for the team here at Swagelok Central Ontario, Atlantic Canada. I'm a professional engineer in Ontario, and a bit about my background here. I have a Bachelor of Science in Mechanical Engineering with a focus on thermal fluids. I've been with Swagelok organization for about 6 years now, and really my focus is on technical support. So hose advisory service, pressure regulator selection, includes high pressure systems as well as seal support system configuration. But today we're going to focus on tube versus pipe. Today we're going to have Hassan Ghoul, an associate solutions engineer with our group here. And a bit of Hassan's background: he has a Bachelor of Engineering Mechanical, and he's been with the Swagelok organization for about 2 years. And again, a focus on technical support. So this includes fluid mechanics, valve selection, regulator essentials, as well as seal support systems. So Hassan will be in the wing to address any questions that you have as we go along here. Now, like Tim mentioned, the focus of today will be on tube versus pipe. So this will include advantages of tube, touch on some thread issues, and then go into some more details on flow, erosion, corrosion in different types of systems. We'll touch on material quality as well as the overall cost when approaching projects. Now, jumping in just on an introduction is about the Swagelok tube fitting. For those that aren't familiar or haven't worked with it too much, just a bit about how the tube fitting works. Now, it's made up of 4 main components. This includes the nut, the back ferrule, the front ferrule, and the fitting body that you see there. The colors are yellow just to sort of show a highlight on the 4 different components. Now, on a very basic level, really, some things to highlight is that there's no special tools required. There's no rotary motion as well. So all that's required is 1 1/4 turns from finger tight. So this is key because the tubing remains perfectly still. There's no rotary motion, and all that's required is the 1 1/4 turn. Now, if you look at the fitting here, we see a section view. This is on the front ferrule here, the longer one, as well as the back ferrule. So really what's being achieved is a long, tight seal area on the front ferrule, and the back ferrule is doing a lot of the work of the gripping as well as the vibration resistance. Now we'll show a short video here just highlighting the simple installation procedure for a tubing system. Now step one is to insert the tubing up against the shoulder of the fitting and to ensure the nut is finger tight. Then to step two, typically we'll mark the nut at the 6 o'clock position. Then as we tighten with a wrench, you'll notice that we'll do 1 1/4 turns, which will end up at the 9 o'clock position. Now that's it, the job's all done, there's nothing more to it. So simply when you're looking at the tube fitting, it's a 2-ferrule mechanical grip Swagelok tube fitting. Now a key thing that we'll touch on a bit later is the vibration resistance that you get from this. There's no special tools. As you saw in the last video, all you need is a simple wrench to tighten the tube fitting, and there's no additional preparation. So threading, no taping of threads, no flaring of the tubing or that type of preparation, and of course no soldering, brazing, or welding of the system. Now when we dive into tube fittings, typically you'll look at the tube pressure ratings. Now tube fitting is rated to the working pressure of the tubing that it's used. So let's go through an example here of the published table. So let's say we have a 1/2-inch system, and let's say you have a 3000 psi system. So what you might select is wall thickness of 0.049. This would result in a working pressure of 3700 psi. Now there would be a 4-to-1 safety factor on top of this, but the actual working pressure would be 3700 psi in this case. Now you'll also notice that there's some shaded cells. So there's a few of these here that are actual shaded region where the rest are white. Now if we're looking at a gas application, that's where this becomes something we need to look at. So let's say, for example, we have 150 psig for an air system. Again, let's focus on 1/2-inch. Now you're thinking 150 psi, you're probably going to be fine with 0.035 wall. So that would have a working pressure of about 2600 psi. But what's really required for a gas system is that because gases are small molecules, they can easily get through leak passive systems compared to a liquid. So what we actually need to do is jump up to that next wall thickness. And this is outside of the shaded region. Now the reason for this is that gas systems require that thicker tubing because it creates more resistance to the ferrule and really results in a longer, tighter seal, so you can ensure that there's a gas tight seal for your system. Now again, one of the main advantages of tube versus pipe is ease of installation. So all that's required are standard wrenches and the job's all done. Now when we look side by side and we touch on some of the advantages of tube versus pipe, one of the primary things to highlight is better strength to weight ratio. And when we're looking at a threaded system, typically you'd be looking at maybe schedule 40 or schedule 80 piping. That's really where the strength to weight ratio is a big difference. But when you look at why you have that extra weight, often people think, well, piping is stronger, it must have a higher pressure rating, it's rigid, it's tough, it's robust. But really, tubing from a pressure rating standpoint is equal, if not better, especially on the strength to weight. So the entire wall thickness of the tube actually contains system pressure. Whereas with a pipe, the reason why you have the thickness primarily is so you can cut threads. So you have all of this extra material here just so you can cut the threads. But when you're looking at the working pressure of the system, it's really defined by the thinnest point in the pipe. And that would be the front of the first thread. Now, obviously, if you're looking at welded systems, you may have some thinner wall on schedule 10 or similar sizes, but we'll touch on some welded systems later on. Additionally, every connection or every joint is a union. We'll touch on again some examples later on. So really, another one of the advantages is fewer connections are required. When you have tubing, you don't have the need to use elbows, introduce additional connections, and each connection is a potential leak point. So when we look at tubing, you have the ability to bend and have that sweeping bend, and you avoid any fittings in this example. Additionally, you're looking at a lower pressure drop. So if you look at this system here, you're having a smoother, more laminar flow. So you have less pressure drops and more flow through your system. Alternatively, you have the sharp corners of the piping system here. And again, looking at the number of fittings or potential leak points, on the tubing system, you have one connection here and one here, and then one here over there. So you have about 4 connections on the tubing system. For this piping system, you have a total of 13 connection points. So again, there's a lot of different things that go into that: leakage, connection points, and even labor that you really save when you're going to bending in a tubing system. Now let's take a specific example side by side. So if we look at an 1.5 inch pipe versus Swagelok tube system, in this case, it's a higher pressure system. So we're looking at schedule 160 pipe, and we're looking at 2 different sizes of tubing. So the wall thickness of 0.134 inches, as well as 0.188 inches for the higher pressure system. So you look at the wall thickness of the pipe, again, there's a lot of extra wall thickness. You're at almost 0.3 inches, whereas you're at 0.134 and then 0.188 as we mentioned for the tube wall. Now for pressure ratings, you're close to 3,000 psi for the piping, and you're up to almost 5,000 psi on the heavier wall thickness of the tube. Now for outside diameter, piping is measured nominally, which means that the actual nominal size of 1.5 inches may not be reflected on a dimension on the pipe. So the outside diameter in this case is 1.9 inches. Whereas for tube, it's always a true OD. So the outside diameter is always true to the nominal size. Now, if we look at the inside diameters, for the SKED 160 pipe, it's about 1.36 inches. Now the tubing is very similar, looking at the 1.23 and a little bit less on the heavier wall at about 1.12. But here's where it really comes in. When we talk about that strength to weight ratio, you look at the pressure rating around 3,000 psi, and you're getting a weight per foot of almost 5 pounds on the piping. Whereas for the tubing, you look at the pressure rating 3,400, 4,900, you're getting respective weights of about 2 pounds and then about 2.7 pounds over here. So it's just a quick overview of a side-by-side comparison, looking at some of the dimensions, the pressure ratings, and the weight per foot. Now, when we look at the different types, again, we talked about the tube fitting over here and really what goes into the installation, all that's required are simple wrenches. When you look to a threaded system, there's taping of the threads. And when you do install a thread, the installation procedure is to install wrench tight. Now, there can be variations in that. You know, if I tighten the fitting to you, wrench tight could mean different things. So there's a lot of variations and factors that can come into that. So there's the threading of the pipe, which we'll touch on, the taping or the sealant, as well as the installation. Now further, there's welded options. So you can see a socket weld example at the top, and then a butt weld example on the bottom. Now there's a lot more that goes into the welded systems, and we'll touch into that in a bit more detail. Now, if you compare these 3 different types, let's specifically look at vibration. Now, there's product testing that we've done for a tubing system, and there's a lot of detail on this slide, but I just want to highlight a few things. Really, the results here are highlighted in the table, but what we're focusing on is the alternating stresses and what's called the stress intensification factor. So as the cycles increase, we measure what that stress intensification factor is in this vibration test. Now, the gold standard for fittings when you look at vibration resistance, that's a butt weld. So you can see here this line is an intensification factor of 1.0. That's a butt weld. When we go to a high quality socket weld, it's about 1.3, so a little bit less than that butt weld. If we look at threaded connections or NPT, it's actually below this third line in this lower region, so it's below 2.3 for the stress intensification factor. Now, where does a Swagelok tube fitting end up? Now, it's in that shaded region. So on average, a Swagelok tube fitting has the vibration resistance that you would expect from a butt weld fitting. And on the low end, it's as good as a high quality socket weld. So some of the benefits in this case, you still get that high performance in vibration systems, but you have the ease of installation. You can assemble it, disassemble it. You have that ease of maintenance that you get from a tube fitting that you wouldn't get in a welded system. Now looking here, here's an example of what that test looks like. So the left side of the tube is fixed. The right side is attached to that rotating chuck. Now this is pressurized to 3,000 psi, and it's a rapid test to simulate vibration that you might find in the field. This goes over a few days and ends up in millions of cycle of vibration. You can see the tube is vibrating back and forth, and this is how we perform that analysis to see how the tube fitting performs in vibration. But really what's happening when we do take that vibration, millions and millions of cycles, and we take it to that form of failure, really how does it fail? Now, if you think about tube fittings, often you'll have the stress riser on the front of that ferrule. So in some tube fittings, that's really where you'll see that stress riser. You'll have a very small point of contact here on the tip, and that's where you might expect fracture. But when you look at a Swagelok tube fitting, you actually see fracture further back on the tubing. Now, why is this and what does that mean? Really what we've created with this back ferrule of the Swagelok tube fitting is a long region, we call it the collating region, where that ferrule is gripping onto the tube. So it's really gripping it, especially in that vibration. You're having that force that would normally be pointed on the stress riser, you have it spread across the tubing. Now this allows it to last much longer, especially in vibration service. And that's why you have the resulting tube fracture further throughout this collating region. Now also, anytime you have vibration, it's important to think about supports. So you want to properly support at a regular interval that tubing. You can see a good example here of routing and tube supports. This is really what you want to see. You want to see bending, you want to have access to the fittings, and you want to have proper supports throughout your system. This can avoid having long lengths that will create and even make the vibration worse in the system. Compared to welding specifically, there's a lot of steps that you avoid when you go to a tubing system. Now, there's fewer steps in the installation, there's less equipment. A big one is the burn permit and the fire watch. So often when you think about the installation costs, there's additional people for fire watch. You might have 2 or 3 people just to do one fitting or one installation. Then there's no air testing on tubing. You avoid purging, passivation, hazmat disposal. So there's a lot of components when you think of a welded system that you can avoid going to a Swagelok tube fitting. So there's no hot work, no welding gases. You avoid weld fumes as well, no shielding. And when you think about the threaded side of things, there's no cutting oils, there's no metal shavings, which we'll see shortly. And you think about confined spaces, if we can avoid hot work and welding, and all you need are simple tools, there's no cleaning that you have from oils. It just makes it a lot simpler and creates the simplicity for the job. And of course, applicable to both ASME B31.1 and B31.3 applications. Now, if we look here at what a typical threading machine would look like, this is really what you're creating. So you can see there's a lot of oil that is used, there's shavings, some oil can go into the pipe itself, and really it's the cleanup of that workspace. You need to account for the cutting oils that are used and make sure that no shavings are left around, and especially that no shavings get into the system so that they would have effect on some of the softer components, which might be a valve seat downstream or some precise instrument. And when we look further at threaded issues, again, we said at the beginning that the installation procedure is to wrench tight. So that can lead to some other challenges because an installer may want to ensure that it's leak tight, or maybe there's not proper engagement, so they tighten it a little bit more. So that can lead to over torquing of the fitting, and especially when stainless steel, you can get galling. So even beyond that, there can be cross threading if things aren't aligned properly, and a big thing is stress risers. So that's why we mentioned that stress intensification factor is below 2.3. Well, really that vibration resistance is poor in this threaded system because you'll have stress risers at different points of engagement, and especially when you have vibration through the system. Now let's look here at a side-by-side example. So this one here is a condensate booster pump. You can see the traditional piping on the left. There's carbon steel painted piping. And then on the right here, you have stainless steel tubing system. Now really, if we look at the before versus the after, it's the number of fittings that's a big difference. 24 fewer fittings overall, and that leads to 86 fewer potential leak points, just on a small system like this. Part of that is that you avoid the use of unions because, like we said, every tube fitting can act as a union or a joint that can be taken apart for maintenance. You avoid the cost of the additional fitting installation, cost of painting, and all the things that come along with that. If we go to another example here, this one is a pipeline pump. So this example here is really addressing the bearing housing. So that's one of the components that often needs to be accessed for maintenance. So if we look at the traditional threaded system over here, anytime the bearing housing would need to go through maintenance, almost all of these fittings would need to be taken apart. So there's a lot of work. It would take at least 2 technicians almost a week just to perform this job. Now, when this was redone in tubing, you can see there's a lot less fittings. All that's required to access this bearing housing is just to disassemble those 2 fittings, swing out the tubing, and you can access it as needed. Additionally, you'll notice there was a change that was made. Normally, the threaded piping would be on the side of the pump around the housing. Instead, a lot of the fittings on the tubing system were actually put closer to the pump. And the reason for this was to ensure that they vibrated at the same frequencies. When it was beside, you would have alternating frequencies between the pump and the fittings, and you would cause more severe vibration and leakage issues. Here, we keep them as close to the pump as possible so that the frequencies remain similar and you have less severe vibration. So really overall, when we're looking at Swagelok tube and tube fittings, it's an engineered solution. It gives you the safety, the reliability, and at the end of the day, it's cost effective, especially when you consider the long run. Now we're going to pause here for some questions. Hassan, do we have any questions that have come through?
Thanks, Phil. Yeah, we have a question from Terry. What size tube fittings do you manufacture? So we manufacture tube fittings with imperial sizes of 1/16 to 2 inches, or metric sizes of 2 millimeters to 15 millimeters. Thanks. That's
Perfect. Thanks, Hassan. So we're going to move on now into the flow aspect of tube versus pipe. Now, I mentioned when you go to a tubing system, especially when you have those long sweeping bends, you stick to laminar flow. So really, what does that mean? When we have laminar flow, it means it's smooth, sweeping flow. It's not turbulent where you have all these little eddy currents. You have the mixing and more mixed type of flow, really mixing among itself instead of having that smooth flow. But what does that really mean? So if we look at the velocity profile, that's what you'll see here. And the actual length of these lines is the velocity or the speed of the fluid. So you can see that when you have laminar flow, at the center of the pipe, you have much longer lines and you achieve a much higher velocity. Whereas when you have turbulence in your system, you're sort of set to a limit and then the velocity can't increase any further. So why does that matter to us? Really, when you have that turbulence, it reduces the velocity, and the velocity is related to the flow. So you reduce the flow in your system. Now we're going to talk a bit deeper into the flow side. So bear with me on this slide, and we're going to get to a key point and finding on the next slide. So there's something called a Reynolds number, and this is a dimensionless quantity, and it's used to help predict the flow patterns, such as the transition when you're going from laminar to that turbulent flow. Now you could use a variety of formulas. An example here is the Colebrook equation, which we're not going to get into, but there's a variety of factors and components in that equation. On the next slide, we're going to show a Moody chart. Again, it talks about Reynolds number, various factors such as the friction factor, relative roughness. But what we're going to focus on in this relative roughness is that E value. So that is the mean height of the pipe roughness. So basically, if you have a smooth versus a rough pipe, that's going to be reflected in this value. So again, this is a complex graph, but what we want to focus on is the chart on the bottom left. This is where you'll see those various E values. So for example, you have something very rough like riveted steel or concrete. You might have an E value or the height of that roughness of about 3 millimeters, which is very rough. You go through wood, galvanized iron, all the way up to drawn tubing, which would be similar to stainless steel tubing. And you have a much smaller E value. So those imperfections or the roughness that you see in the material would be much smaller. So now the point that we want to make here is when you're looking at steel piping, your typical commercial steel pipe versus a stainless steel tube, there is a measurable difference between those roughnesses. Now, this doesn't mean that you're going to have the ratio of differences when you're looking at the smoothness, but the point is that there's a measurable difference when you're looking at the smoothness of a tube versus the smoothness of a typical commercial pipe. Further, now let's look about pressure drop. We talked about elbows and how they have effect on the pressure drop. Now, the way we can show what that really means is by using the equivalent feet method. So let's take an example here. Let's look at 1-inch tubing. Now, if you had a 90-degree elbow, what you would actually have is a pressure drop that's the same as if you had 4.5 feet of straight pipe. We always compare back to straight pipe and the pressure drop that you would achieve. Instead, if we look at a bent tube, so that long sweeping bend, it would only have the pressure drop similar to 1 foot of straight pipe. So if you think of a system that has dozens or hundreds of elbows, it's the same as adding many hundreds of straight piping or tubing and the pressure drop associated with that. Now, if you're looking at elbows, the same or similar pressure drop, you're still going to achieve whether it's a piping elbow or whether it's a tubing elbow. So the key is, whenever possible, try to go to that bent tube. You have those long sweeping bends, and you can really avoid a lot of the pressure drop that you would have in the sharp elbows of that piping system. Really, what's the result? If you have lower pressure drop, you can have reduced hammer or shock depending on the system, and really lower pressure may be required. In many cases, if you have a supply pump for a system that has many feet of piping or tubing, you may have the ability to lower the pressure that's required from that pump. Maybe you can select a different pump that may have other cost efficiencies for your system. Now let's look at another topic here, looking at corrosion and erosion. Now again, there's a lot of information here, but we're just going to focus on a few components. Now this table talks about different variables, and this was taken specifically for boiler feed water. So in this case, each variable has a different effect. So for example, if you have a higher velocity, that's going to increase the erosion or corrosion in your system, and so on as we go through the examples. But what we can focus on and what we can control in this case is the geometry, so tubing sweeping bends versus elbows, for example, as well as the components of chromium and molybdenum. So we talked a bit about that painted carbon steel system, and we can compare that to stainless steel. So what we're saying here is the component geometry, it creates more turbulence with elbows. So that turbulence affects and creates more erosion and more corrosion in the system. And again, here, if you have lower chromium and lower molybdenum, that's going to increase the erosion and result in more corrosion. So again, if we look at the typical comparison, if we're looking at 316 tubing, which is most commonly used, versus your traditional carbon steel piping, you have that less turbulent flow, and naturally you have higher chromium and higher molybdenum content. So overall, if we look at tubing versus traditional piping systems, you're going to achieve a longer service life and really less maintenance. So a lot of the cost savings and the performance you're going to achieve over that longer life, less maintenance, and really just have a better performing system. Now we'll pause again for questions. Hassan, anything come through?
Thanks, Phil. Yeah, we have a question from Omid, and it says, wouldn't the bending section be exposed to more pressure and therefore cause failure? So in conclusion, bending does not affect the pressure rating of the tubing itself, as long as you're maintaining the adequate bending radius, of course. And based on the pressure burst tests that, if you ever, had the chance to do it, you actually see that the failure does not actually happen at the bend. It will happen somewhere else. Phil, do you have anything you'd like to add to that?
Yeah, sure. Thanks, Hassan. So great question there. That is a common question that we receive. But when you look at tubing itself, tubing is actually annealed and a much softer material. So when you bend tubing, what you're actually doing is work hardening and reversing that annealing process, and it actually becomes the strongest part of the system. So like Hassan said, if we did take a tubing system and overpressurized it all the way up to that burst pressure, you actually would see a tubing system would fail in the longest straight section, and those tubing sections that are bent on the sweeping bends, those would actually be the strongest sections and would remain untouched. Thanks, Hassan.
Thanks.
So let's move on to the next section here, just touching on a few more topics. So when we think about compliance, that's often a question that we see. CRNs, of course, is important in Canada, and for a tubing system, you achieve all of these things. TSSA compliance in Ontario, ASME B31, B31.3, ASTM, ISO quality program. A key thing we always highlight as well is the US Navy. They have the ASTM F1387. Now, this is a very stringent series of tests that has gone through as well. And then other various certificates, CSA, TUV, PED. The point is there's a wide variety of compliance because we understand that that's an important component that may be required for different systems. Now, another thing is material quality. So we touched on this a little bit when we were talking about erosion and corrosion. But one thing to really highlight is what we've done at Swagelok to take it a next step further. Now, if you look at 316 stainless steel, most commonly used type of stainless steel, these are the variety of subcomponents of the different alloys. Now, what you'll notice is that for chromium and for nickel, there's actually a range. So as you might guess, a lot of the common industrial components that you'd find, in order to save costs, they go very close to the low end of those values, which means it's still compliant as 316 stainless steel, but you avoid using expensive nickel and chromium. So you might see 16.1% chromium and close to that 10.1% nickel. But really, we find that in certain corrosive environments, this has a drastic effect. And there's certain percentages that you really want to hit to ensure that performance. So for all Swagelok tube fittings, we'll have a minimum of 17% chromium and a minimum of 12% nickel. So this still remains compliant to the 316, but it elevates those so that you can ensure that performance. So an example that you'll see over here, this is another general industrial component, non-Swagelok, that had 10.1% nickel. Now, when we put it through a corrosive environment with high chlorides, you can see that there was cracking from corrosion and failure of the component. Now, if you took the Swagelok component, which maintained that 12% nickel, it did not experience any of this cracking and failure in that same corrosive environment. So beyond just having those chromium and nickel levels, it all starts with the raw material. So we talked about the performance of the fitting itself, but there's a lot that goes into the material and the feedstock into your component. So for one, all forgings and bar stocks are used for pressure bearing and pressure retaining components. We do 100% ultrasonic examination, we do eddy current analysis, and we always do random sampling. So we have an independent lab, and our lab holds ISO 17025 accreditation. And many of our components have nuclear requirement as well. So 10 CFR 50 Appendix B quality program, which really holds our material to a high standard. Beyond that, if we do have any outside machining for components, we provide the material. So controlling and really having a lot of details and quality into the material supply chain is critical to ensure the performance of components. Now, along with that comes traceability. So especially when you're looking at nuclear or other industries, there may be PMI testing and really having that integral traceability, whether it's to ASTM, ASME, NACE components, NAFTA, various military standards, NORSOC, and 3A for sanitary applications. So what that all builds into, whether it's the design of the material, it's the limited lifetime warranty. So when you do have a Swagelok tubing system, you can be sure that all materials will have limited lifetime warranty on material and workmanship. Now, let's go through some cost analysis here and give a project example. Now, what you've seen here was actually put together by a contractor. They were looking at a steam heating system, 1 inch in this case, and they wanted to compare welded piping versus a Swagelok tubing system. Now, you'll notice material costs is a little bit less on the piping, $3,600 in this example versus around $11,000 for the Swagelok. But if you look at the number of fittings here, you're looking at about approximately 150 fittings versus about 90, but the number of joints, over 300 joints versus about 200, and especially on this welded steam heating system, you're almost at 500 welder hours. Now, this was an example rate that was used in the example by the contractor. But when you compare 480 hours versus 32, you can see that it really adds up quickly. Then when we go to the pipe fitter hours, over 700 compared to 200 on the tubing system. So if we look at that side by side, really it's that lower total installed cost. So that piping system was about 135,000, including the material and the labor. Now the labor was actually 97% of that cost. The material was only 3% of the total project cost. So if we went to an example here where we save 74%, that's where the labor was actually 32% of the cost. So the materials is 2/3 of your value in the 35,000. So really, not only are you saving money, but you're investing in your system. So this 2/3 of this cost is actually being maintained in the system and is going to ensure the performance. Whereas in the piping system, you're really only spending 3% on the materials and the quality that you're going to have for the long run of the performance in that application. So really, when you're comparing side by side, going to a tubing system, you are paying more for the material, but we talked about the material quality, the performance that you're going to get from that material, and you're getting the savings in a variety of ways. You're saving on labor, there's less fittings, there's less consumables and equipment, especially when you're looking at welded. There's less leaks, not only in the long run, but when you're looking at a startup. There's less downtime, and of course, in the long run, you're looking at your MRO, your maintenance, repair, and your operations. Your costs are going to be lower in the long run when you're using that tubing system. So for that project support as well, what comes along with that is installation training, as well as the tool. So whether there's a bender that you need, this is an example of a benchtop bender, which is used for the larger sizes of tubing, or a pre-swaging tool. So if you do have larger sizes, this pre-swaging tool can help pre-swage the ferrules to make the installation easier. So along with the tube fitting, and like Tim mentioned at the beginning, when you look at the Swagelok distributor network, whether it's locally here in Ontario or Atlantic, Canada, or globally with a local distributor, you're going to receive that on-site support, the technical expertise, the engineering services and the support like you've seen today, as well as validation testing and training. So it's that complete project support that you're going to receive, not only the quality from the tubing and the tube fittings and the other components. So we'll stop again here for questions. Hassan, do we have any final questions here?
Yeah, thanks, Phil. We have two questions that are actually, they're asking us, about the previous section. And the first is, and they're kind of related actually. The first is from Ajith, and he says, what are the types of corrosion avoided in tubing compared to piping? So what Phil touched on when he talked about erosion, corrosion, are some factors that are different between tubing and piping, and that could lead to different results if those variables are changing. And those factors are geometry, the surface roughness itself. It does affect the turbulence, which I will talk about in a bit while answering the second question, and the chromium and the molybdenum content as well. So that affects the corrosion performance, and that leads to a difference in that corrosion performance between tubing and piping. So to answer the second question, and it's from Anonymous, why is the surface roughness of a pipe more than a tube? Are they not the same? Can a pipe not be bent into a tube? So the reason is, the reason is the tubing and the piping have different surface roughnesses is actually the way they're manufactured. The micro structure on those surfaces are different, and that leads to a different epsilon value, or the surface roughness that we saw in the Moody chart, which leads to a different friction factor. So cauldron tubing has a different surface roughness than a tubing that's manufactured in a different way, and usually pipes are made differently than cauldron tubing, for example, and they have much higher surface roughnesses. So they are the same material, but they are manufactured differently, and that definitely affects the turbulence as per the Moody chart that Phil touched on earlier. So I hope that answers the question. Can a pipe not be bent into a tube? Again, it's more than just a structure. It's the way it's manufactured, and the dimensions of the wall thicknesses, and not having to thread it, So that's also a key difference. Thanks.
All right, thanks, Hassan. Great questions coming in from everyone. And you can always reach out later on with additional questions. When you talk about corrosion, to the question there's a variety of corrosion you can see, whether it's general corrosion, stress corrosion cracking. Now this depends on the system and the material, but primarily when you look at the tubing in the 316, and especially even the erosion that you'll see in a general application. Now, just to wrap up here, Hassan and I were here to help you today. When you look at our local team, you have that engineering and technical support. So here's our engineering support team that you have locally. But again, for those that are listening in from other regions, you can have additional support for that engineering and technical team from your local distributor. Thanks everyone for your time, and I'll hand it off to Tim to wrap up here.
Thanks everyone for attending today's Tube versus Pipe Tech Talk. We're always looking at ways to improve these virtual sessions. So you can see on your screen there's a link for webinar feedback. Feel free to follow that link, and any feedback you can share would be much appreciated. And Cam's also posted that in the Q&A for you. So we'll hold there if you want to click and provide your feedback, and we'll also email that out after this session to the attendees. But thanks a lot, everyone, for attending today. We have some upcoming sessions as well. Look forward to talking more and helping to share some knowledge. Thanks, everyone, and have a great day.